Good afternoon, good evening, wherever you are, and thank you for joining us today. My name is Mohammed Yaqub. I'm the MICCAI 2026 General Chair, which will be in Abu Dhabi in the UAE, and I'm delighted here today on one of the MICCAI industrial talk sessions where I'm joined with Richie Zsámboki from GE Healthcare, who will be giving us an interesting talk on about the optimizing ultrasound image similarity search. Richie will present himself in more details, and I'm sure you'll hear more about him. Before I move on to Richie, can I please ask everyone to, if you have any question, please share it on or put it on the Q&A box, and we aim to answer as many of these questions as possible at the end of the presentation, which will last approximately 40-ish to 45 minutes. So after that, we'll go through the questions and answer them. So if you have any question, feel free to write in the Q&A box, and Richie and I will go through them at the end of the presentation. It's a pleasure to have you, Richie. The floor is yours.
Thank you, Mohammed. So hello, everyone. I'm Richárd, Richie for short, and I will present to you about similarity search and how it can be used to optimize ultrasound image similarity, and what kind of published works we have done in recent years. Okay, so I was muted, so I realized. So hello, everyone. Again, so I'm Richie for short, and I will talk about ultrasound image similarity. And I will just briefly talk about the agenda, so you will know where we are headed. So after some introductions, personal and project level introduction, I will talk a bit about the necessary foundations and methods to understand the three sections about published works in this domain in our project, and I will close up with some future slides and, of course, the Q&A. About myself in a little bit. So I'm a senior data scientist, senior staff data scientist at GE Healthcare. I'm located in Budapest, Hungary, and I'm part of a quite large AI team here. I have more than 10 years experience in deep learning. I started my career with autonomous driving perception, segmentation, lane parking slot detection. So this is where I learned all the tricks and trades of deep learning and how to research and develop models and applications that can be used in real life. And right now I'm focusing on building clinically useful AI. In my more than 6 years of experience in GE Healthcare with Healthcare AI, I worked with organ segmentation, tumor and anomaly detection. I participated in the breast challenge in this task. I developed view classification models, and recently I focused heavily on image similarity search, which will be the main focus of today's talk. So to understand where we developed, where we researched the upcoming works, I will talk about the project which housed all of this. But first, what is the main clinical need behind everything we did? Is in ultrasound, obstetrics and gynecology, screenings poses a major cognitive load, and there's a significant medical impact to do this. And only in Europe, there are multiple millions of examinations performed each year. And if there is any unusual feature or anomaly seen during these routine scans, there is a request of a secondary or expert scan. And it's an issue in many regions that there is a huge need for these experts. And theoretically, these initial pregnancy scans could be improved with proper assistance. A possible solution can be to leverage a composite AI solution combining image recognition AI with ontology-based reasoning, and these two together can bring us human-readable guidance with expert-validated galleries optionally during the scan. And this can help the user, even a novice user, during the first scan to collect all relevant images during the scan and analyze these images to achieve diagnosis. And hypothetically, this could make this could be alleviate the need of the second expert scan. Just a few words about what ontology is. This won't be the focus of the talk, just to understand this composite AI framework. The ontology is a knowledge graph of terms in ultrasound screening, disorders, findings, anomalies, and technical elements like views and the probe that was used during screenings. And apart from the list of these elements, the interconnectivity between them provides us the means of reasoning how to provide guidance to the user during screenings. Unfortunately, I cannot go more into more detail because that would give us another 30 minutes. But let's jump on this next slide, where I will talk about just briefly the project itself, which was created to develop this solution from the previous slide, to integrate this knowledge base and image recognition to guide operators in real time with decisions that can remain human readable. As you see, it was a project with many partners, financed initially by EIT Health. And you can find out more if you visit the website sug.org. So now that we know what project we were in, let's talk about the necessary foundations, methods, how we encode images, how we search efficiently, and how to evaluate the clinical relevance. So a more detailed problem framing from than the project slides. So during ultrasound screening, the main task that should be performed is to distinguish the acquisition plane before capturing an image, perform measurements, identify findings, anomalies, and of course set up diagnosis. This is just a very high level list of tasks that we are interested in, and Similarity Search might be able to support all of this with proper development. The diagnosis itself deserves its own slide, because it's a very complex process requiring, among others, images, multiple images from several acquisition plane, identified findings, anomalies, measurements during examinations, the medical history of the patient, and the last but not least, the experience and insight of the user itself, the expert itself. And it's very important to mention that relying on just a subset of this is very challenging, and you might not reach the same diagnosis than taking into account all inputs. And it will come back later that, especially if we just looking at images themselves, the single image or even a set of images rarely maps cleanly to diagnosis. So it's very important to take this into account when measuring and evaluating all these search solutions. And this is a different problem than the screening itself, but it came up even during our project that for medical development, medical research, there is always data need. Large expert label data set are usually needed. And in most projects, we realize that labeling is most of the times slow and costly, and even acquiring expert help is challenging due to these experts are, their time, and their time is quite valuable, so they're not always up to a task of labeling. So a solution to alleviate this is to help the experts by creating a pre-labeling assisted loop where they can create the same quality output but much faster. I will talk about this in more details later during one of the works. So image similarity search on a very high level can be considered a content-based image retrieval, or CBIR for short. So this is a quite popular research area. It's about how you search in a reference database based on a query content. And in high level, you can imagine it by having an offline and an online phase. Offline phase is usually encoding the raw data, in our case, reference images, and build up an index, for example, a search tree. And during the online query, you encode your query data, query image to be in the same feature space than your reference data, and then you perform some structured search method to retrieve the top K similar images. And one of the most popular ways of encoding these images is by deep learning, by neural networks, and even more specifically, vision transformers are heavily used in these solutions. So the general idea is to use embedding vector from image encoders. So this, if you are familiar with deep learning, there are usually, especially in traditional convolutional neural networks, there is a latent space representation, like you can consider it the bottleneck of the neural network. So if you take your representation from there, that is a good embedding vector, and can be used for encoding. And even in our experiments, we used a traditional convolutional neural network as one of our candidates. So you will see how that fared with others. But we mostly focused on vision transformers. Vision transformers are very promising because these are quite powerful alternatives to traditional networks because they can capture global relationships using their self-attention. And these are very effective for generating high-quality global descriptors, even without retraining the models, because large data sets were used to training them, and the robustness and generalizability is quite surprising in most of the cases. So even when coming from a natural image domain to medical domain, they keep a lot of their generativeness and robustness. And you will see later that this is actually the case. So we can get robust descriptors for retrieval if we use this kind of methods. So some example that we selected. So this list. When this publication was made, I think Dino V2 just came out. So that's why we used these three. So Dino and Dino V2 are self-supervised vision transformers. And so these were trained without explicit labels, and they learn by matching different views of the same image. SEM2 or segment anything model 2 is a different kind of vision transformers because these were trained for vision tasks, like in the name segment anything, but the encoder part of it can still be used for our case. And DreamSim is so we use two things from the DreamSim work. One is they created the model itself with an ensemble of different models, but most importantly, they developed a metric based on human judgment of similarity, and in theory it aligns quite well with what people believe or perceive as similar. And it will come up later when we talk about how different pixel metrics can be used to measure similarity. Once you have your encoding and your feature embeddings, and you will have all your reference data and query data in this feature space, the next task is to actually search in this space and make sense of what you are doing. The goal itself, as before, is to get or retrieve top K most similar images based on a query image. For large data set of relatively high dimensional feature space, structured search methods are recommended. For one of the example is search trees, which are algorithms that work by dividing the dataset into smaller parts, enabling faster access and then retrieval of data features. That we tried out two specific examples: KD tree, which divides the dataset along each dimension recursively until it reaches the leaf nodes, and ball tree, which creates hyperspheres of equal size and radius in your database. These are quite fast to build up on the offline phase, and the query is very quick with both. So in our current use case, where we don't have a huge database, we stick to search trees, more specifically KD trees. But it's worth to mention that a very popular method that people use, especially when you arrive in a big data domain, is vector databases, or vector DB for short. And since these are retrieval systems designed for higher dimensional spaces. So they use binary search trees for storing vectors, and these are very efficient in querying extremely large databases. So we put a mention everywhere that if we expect our data set to grow, vector databases should be revisited later. Now that you have a high-level overview of what image similarity is and what kind of methods can be used to create these image similarity search workflows. Let's talk about some example use cases. Among others, and focusing right now on the medical domain or ultrasound domain, I talked about the annotation part. So to accelerate annotation, by leveraging already annotated similar images are one key use case. The second is quality control. So a lot of the times explainable AI comes up as a hot topic. So how we explain, how we enhance, or how we prove that our AI output is correct. If you have an already verified and expert review reference gallery, you can put these similar outputs to the user, or if you don't even show it to a user, but you can design a verification pipeline in the back that use Similarity to cross-reference your AI output with all these references. And the third one, which is the key target of our works, is decision support. Is where you have some decision support system, like the composite AI one I talked about in SUOG, and you can enhance these recommendations by looking up example reference images, which is quite important for the user at that current stage. It might come up multiple times, but I wanted to create a big slide at least one time here, that similarity search and all these systems I talk about are just decision support with reference galleries. So these are not diagnostic system. So we do not make diagnoses based on similarity search and images alone. It will come up later why we are not doing this, but it's important to keep in our mind that the diagnosis itself remain clinician-led, whatever tools we are using. So I talked about how many inputs required and how many factors can affect the diagnosis. So all of these should be taken into account with the expert using all their knowledge and insights. And what we try to create here and try to propose here are tools, additional tools on that tool belt that they can use during this process. So let's start with the first published work from our project in this topic, the AI-assisted view labeling, which will address how we make annotation more efficient. So as I already mentioned, manual labeling, any kind of labeling, is time-consuming and costly, and finding these experts can be problematic given the complexity of the task. But it's clinically quite relevant to solve this issue because all medical development and research needs at least some data, but the more you have is the more opportunities you have in your research, and there are multiple approaches how you can elevate this one. One is, okay, let's focus on the annotation process itself and make it more efficient to be able to generate the same amount, the same quality of data with less effort. And I will focus on that. Of course, there are other ones like how you generate your own data synthetically, but that is out of scope today. So the approach we devised is you start reading this loop at the top. So you start with the seed data that you annotate with your experts, and then use the labels on the seed data, extract the image embeddings of the seed images, and then propagate the expert labels with traditional classifier methods. For example, nearest neighbor search performed on your feature space, and then select a subset of what you propagated and review it by experts, at least a chunk of it. And then, of course, the seed step can be ignored later. So because if it works, even if only the reviewed propagated labels are refitted or returned to the image bending sanction. And now you do the propagation again, but with additional images added in. And in theory, this loop, with a human in this loop, is a very efficient way of doing labeling, because with the help of these vision transformer, these encoders, and image similarity methods, you can leverage the already annotated data to speed up the unannotated part. And we did two measurements. One was a simulation where we simulated a perfect user who is able to label and review correctly, and we assumed that labeling an image from scratch takes more time than just reviewing and accepting an image. And we also assume that spotting a mistake and correcting a label can be slightly slower than annotating from scratch, because you have to correct it, not just put a label on it. And with these assumptions, we simulated that there is a 25% reduction in annotation time. And the same was proven during a real scenario where we, apart from time save, we actually measured the accuracy of the loop. And how you read that bar plot is important. So we measured the accuracy of the propagated labels after each iteration. So the expert provided a seed data set, and the first propagated batch we handed back had a 60-ish% accuracy. Then after review, we feeded the reviewed data back and created a second batch with almost 90% accuracy, and the third batch was more than 90% accuracy. So even just a few iterations, these were like a few hundreds of images. So even at the very beginning of this process, we saw a quite big increase in accuracy. And of course, the more accurate you are, the more quick you can progress, because it takes less time to review batches. So this human in the loop pre-labeling reduced expert time in our case while maintaining high accuracy. And you can check this work. I put a link here to ICUOG 2024. We had a poster with this work. So next up is model benchmarking, because as I said previously, although we are using vision transformers in general, because they are robust and has a very good global representational capability, we still need to benchmark the different models, because multiple encoders can have different strengths. They had different training data. They often have slightly different training methods or architectures. So there is no one size fits all model here that can best every other with every in every use case. And it's especially true in medical domain, because none of these models that we will talk about right now were trained on medical data. So it's not obvious which will outperform the other. Even if we stick to one use case like ultrasound similarity in our work, if we consider different stages of our database, like early pregnancy, first trimester data compared to fetal examinations. It's the same network that proved us a very good similarity capability for early pregnancy might not work for fetal, and vice versa. So a careful benchmarking and evaluation is important here. And we might need to make task appropriate choices. So we won't end up with one model that beats all, but we may need to choose our models according to the task. And of course, the clinical relevance here is that there can be several clinical uses where we can employ similarity, like providing support for view acquisition, providing support for findings, anomalies, and of course providing support to make diagnosis. And all of these might require different models, different encoders. Our approach was quite simple in a high level. So we implemented a basic similarity search workflow and executed on a large label data set we have. So we have almost 5,000 images from first trimester early pregnancy data, and 3,000 fetal data. And we used this set as our evaluation set. We considered 4 vision transformers, 2 from the Dino family, the Dino and the Dino V2, 1 from the segment anything model family, and the DreamSim encoder. And for reference, we also tried one of our own models, which was a convolutional neural network, a residual network, trained for view classification for early pregnancy. And this was to check our hypothesis that
Richard, we lost your voice a bit.
was a slight issue with my mic, but it should be okay right now. And we also evaluated multiple search methods. So I already spoiled this one that we selected KD3, but we evaluated all. So So this was on what were our metrics. So for this search methods, I didn't put it here, but for the search methods, we just measured the inference time required to set up the offline indexing and to run the queries. But for the actual similarity, how we measure this one, we basically did three different groups of metrics. One was that we consider the clinically relevant metric is we consider clinical relevance to be correlated with the matches between labels between query images and top K results. What this means, it might need a little more explanation, that in our data set, we had categorical labels of views, which are basically the acquisition plane or the organ. And we had labels for findings on an image. So these are usually anomalies or findings based on measurements. And we also had a diagnosis label on these images. And since we only used our data set with labels, we can assume that we will have the label information on both the query image and all the images in our gallery. Or I call gallery here. It's the top 10 result of a similarity search query. And we checked each individual image on the right and checked if the view label matches with the view label of the query image. And this is the example you see detailed in this table. And we noticed that you can immediately see on the right that all of these images are very similar to our query image. But if you consider the actual view of the image, you see that this is a sagittal cervical fetal spine, and you have lumbar fetal spine, thoracic fetal spine views on the right. So this means that the actual view matches are quite low, because in our data set and in the medical domain, this categorization is very fine, on a very fine level. So you have these fine differences between different spine views. So we leveraged the fact that we have a detailed knowledge base of all of these terms from our project. So we checked, okay, what about the group level matches, where we consider each fetal spine view a fetal spine view as a group, and here we immediately saw that, okay, we have 8 fetal spine in these 10 images, which corresponds to the fetal spine category of our query image. So we made this choice because these images, which are different spine views, but still spine views, and this can be said for many other organs, can still be clinically important and relevant, even though it's not 100% accurately from the same acquisition plane. So it's important to measure this metric as well. So this was the clinical label match statistics. We also measured pixel-based similarity metrics like histogram score, mean squared error, and such. And as I mentioned on an earlier slide, we leveraged the DreamSim scores, which are devised to correlate well with human perception. Of course, this I put some asterisks here and there because using DreamSim scores can bias the evaluation of the DreamSim encoder itself. So of course, these measurements should be ignored or not taken into account when selecting models. So I don't want to go over every number here. I just put it here for reference if you want to later check our evaluation. And of course, you can check our paper. I will. There is a link to the paper with even more measurements, but just that's a summary. So we partitioned our evaluation into two main parts: one for early pregnancy and one for fetal. This had multiple explanation why we did it this way. So this partition was present throughout the whole project. So even though we talk about pregnancy screening as a whole, early pregnancy, especially in our project, had some unique factors that we needed to separate the two in a lot of the cases, as for example here. So we checked for early pregnancy how the models performed, and here we see that one of our hypotheses became true, is that the network that we specifically trained for classifying views, no surprise, so using the feature space of this network, we can get the best similarity performance considering view matches. So that there is no surprise here. It was just good to see it come back. But for other purposes, like to get diagnosis match correctly or to get finding match correctly, these task-specific networks fails to perform on the same level as the vision transformers. So that's why I said there is no one size fits all. For diagnosis, we found that the Dino model was especially great in searching similar diagnosed images. So here, how you can understand this number, this means that, and maybe I forgot to put here an explanation line at the top, that from a top 10 gallery, so a top 10 image similarity search, how many images on average has the same diagnosis as the query image. So we take a huge number of query images, we run evaluations, and on average, if we take a random early pregnancy image, we will get around 4 images in the gallery with the same diagnosis, which is a great advancement compared to just randomly sampling from our data set. And we always see that we get almost twice the number of relevant images in our gallery, given an application which uses this feature. And with findings, the situation is even more better, and it's with a different encoder. So you can see that Dino is close second, but DreamSim came up first with findings. You can see that if you just looking at random images from your reference data in our early pregnancy database, you will see 1 in 10 images which might have the same finding or same anomaly that your query image. But if you search with the similarity methods in your database, you get more than 3 images with the same findings. And these may not sound that crazy numbers, because you want find 10 out of 10, but still this is a very complex process, these examinations and diagnosing. So even just 2-3 extra images might boost the process in a way that the user will reach the diagnosis faster or with better accuracy. So we did the same for fetal, with the exception of findings, because our finding database or finding labels in a fetal database were quite noisy. So we found that it was very hard to make sense of it. So for the sake of this work, we left out finding evaluation and focused on view and diagnosis. So with view, one thing to point out that our model that performed especially great on early pregnancy images now fails to perform on fetal ones. That shows that even though for one specific use case, one specific domain, you might get a huge benefit of using that specific models, but as soon as you change anything, it will be outperformed by these vision transformers, which were never even seen medical images. So that's an important observation here. In fetal, Dino was a close second, but the DreamSim encoder, which again was trained on using an ensemble of other models, became first in all categories. Maybe in Dino, Slav was slightly better in the diagnosis, but worse in the group match category. And here I will talk about it more detail in a later slide, but just to point out that you saw that we had these above 3 similar images with the diagnosis matches, but with fetal we see less than 1. And I will discuss this phenomenon later in the limitation slides, just with the mental note here. So as a summary, the end of this benchmarking resulted in KD3 selection for search methods and DreamSim and residual network for view classification, and Dino DreamSim for other tasks. But the takeaway is that model choice highly depends on what your target is, so you have to choose your model carefully after evaluation. And what happens, and this is a very interesting addition to all of this, what happens when you put the user in the loop? So similar images are not always clinically relevant. I talked about it in the diagnostic process. So one image will not correlate with the diagnosis. So incorporating the experience and insight of the user can improve performance, and most of all can improve the acceptance of these tools. If the user feels that he or she is in control and adds information, and the information affects the outcome, that is a better tool than just automatically do something with images. So the main idea is that the user provides annotations, and these annotations, along with the acquired images, are combined together in a combined feature space, and this combined feature space will be used for image similarity search. And we devised one experiment where we took the Dino encoder from our previous experiments and used our view labels and finding labels and created human readable sentences describing the images. For example, this ultrasound image is an image from the uterus and has this and this finding an anomaly. And we encoded these sentences with BERT and used the combined feature space of the Dino embedding from the image and BERT embedding from the label to perform the same similarity searches. And we measured the diagnosis match from our benchmarking work, and we also performed expert review of the results. And we saw that the average diagnosis match from looking at the top 10 images, starting from 38% if you're using only images, shoot up to 46 and 75% if we added all other informations. And this means that if the user starts labeling the query image and labels the image with the acquisition view and labels the image with findings, the gallery of reference images, the quality of these reference images improves significantly. And even I think three experts judged in 70% of the cases that multimodal results are more clinically relevant than the results using only images. So this is a way to elevate the problem of images not always corresponding with diagnosis, because if you consider images and findings and views, this set of information is more correlated with the diagnosis. So we saw that. So this interactive multimodal loop substantially improves meaningful matches. It is not yet available on the website, but I put here, we presented this work on ICOG 2025. So what's next, and what were the limitations and lessons learned during this project? So we saw that on all parts of this project that rare views, rare findings, rare diagnoses are very hard things to crack, because if you have just a handful of images from a finding or a diagnosis, to query them out from a large database is especially hard. So sometimes we even needed to remove them from the database and say, okay, these are limitations of our solutions. Weighted metrics helps, or weighting solutions can help, but it's still a problem. I addressed this multiple times, but diagnosis linkage is an issue that single image similarity does not map cleanly to diagnosis. And we saw that multimodal input already improves it, but doesn't fully replace the clinician, because the clinicians still have more information than a multimodal input can simulate. Annotation quality affects evaluation and model selection. We saw that, especially in the finding labels of the fetal data set, that if it's inconsistent or noisy, it's very hard to evaluate models with. And as we saw in the residual network experiment, that if there is a domain shift, certain models, certain encoders may not generalize well across different scanners, different protocols, or different stages of ultrasound examinations. To address some of these limitations and just to list some potential future works, we can extend our data set with some targeted labeling, or trying out synthetic data to elevate the problem of rare cases. There are multiple ways of tackling this. Since the work we put in with the benchmarking, there were more encoders released. So keeping track of it is a continuous future work of such development. Of course, once you have enough data yourself, you can train a custom feature extractor, which is always tricky, as you saw in a residual network, which was a quite small network with a lot of problems. But even if you increase your network architecture, increase your data, you might still run into generalizability problems. But this is obviously a nice future work if one have the data for it. And one thing we didn't do is the interactive methods I presented. The expert review for that was just an offline review where we pre-generated results and they evaluated in an offline way. But it would be nice to see an interactive method lively evaluated and tested. I want to thank a lot of people, because I did not say it enough times during the presentation, but this was a group effort with many people involved, both from GE Healthcare, both from SOG partners and other institutions. And I also want to thank the MICCAI Industrial Talk Series host and to provide a forum for me to present this to everyone. And I think we can start the Q&A, and I'm up for answering the questions you have.
Okay, thank you, Richie, for the interesting talk. And we have a few questions. Please feel free to write in the Q&A box, everyone, and I'll go through these questions one by one. But actually, I have a question for myself. Can you just elaborate a little bit more on the clinical need of search, especially on the case where fetal ultrasound is a real-time acquisition? You mentioned at the end interactive assessment would be, or real-time interactive assessment would be nice. But if I am a sonographer using that on a real time, Why would a technology like this help me?
Um, so it depends on the use case. So we can envision a use case where you process all of this data offline separately from the examination. So that is not obviously that's not real time, but once you have your collection of images and you just want to cross-reference that with a large reference data your hospital might have or an application might have. And On a real time basis, especially with fetal ultrasound. The fetal ultrasound is usually quite long process. You know, the clinicians do the measurements while the examination is happening. So in that examination, the patients are not that bothered, maybe not that bothered with an extra minute of looking at gallery of images, and while the doctor is doing the measurements, he or she can take into account all the reference images, and then with the measurements observed and the reference images checked, the notes they can might be of better accuracy.
Okay, thank you. So let's get started with some of the questions. So the first question is, Hang Dong says, thanks, I might have missed something in the talk. How is ontology used in the image search?
Okay, so I mentioned that slide that the ontology will not be a key target of this talk, but we used it indirectly because our data set was labeled with ontology terms. So that's why we were able to for example, calculate match level, group level matches, that for each view category or finding category, diagnosis category, we know the parent group of that diagnosis. For example, we knew for each diagnosis, we knew if those were a brain disorders or a fetal heart disorder, and so on. So we leveraged ontology in this way to create a multiple level of evaluation, match evaluation. But apart from that, in this similarity work, we did not rely on the ontology. So the ontology itself is on a project scope level.
Makes sense. Okay, thank you very much. Next question, could there be other ways to measure the accuracy of the similarity search? I'm thinking not measuring match of diagnosis, but something else that also corresponds to partial similarity. Or is the diagnosis match the main point here?
So that's a very great question, and it highly depends on the task you want to solve. Because if your goal is to create an annotation tool which is great for let's say view classification, then yeah, that's the view match is the metric you want to select. If you want your similarity search to perform well in this decision support system, yeah, you will have to go to clinicians, go to experts, and collect information what is actually the most important. We found that the goal would be to have the diagnosis matching with the reference gallery or the findings. So these would be very nice examples. So in a clinical domain, I think that is my answer. Of course, I did not talk that much about pixel similarity because we found at multiple times that pixel similarity does not correlate with clinical similarity. It correlates with view similarity. So similar views are often similar on a pixel-wise, but pixel-wise similarity stops there. So yeah, you have to carefully choose which is the most important for your task, and then select that evaluation metric.
Okay, thank you. Next question, with respect to the experimental results, I somehow think that the number of matches within each batch could be biased. Because, for example, even though there are 5 matches in a batch, they can be like in position 6 to 10 positions, which does not seem better to other method with 4 matches, but those matched ones ranked 1 to 4. Are there any more detailed experimental results for your comparison in slide 28 to 29? It's a long question, so
Okay.
maybe we can go back to slide question 29, 28.
29.
So are there any more detailed experimental results for your comparison on these 2 slides?
On these 2 slides, I did not prepare with more detail, so this was a poster. So obviously, there can be some bias. I might not understand fully the logic in the question, but yeah, these top 10 results are often brings up. So evaluating all of this work was merely the highest complexity of task in each of this work. So we realized quickly that to evaluate similarity and how good is a similarity result, it's not a clean-cut question like how accurate is your label or how accurate is your segmentation. So evaluating those models are quite straightforward. Evaluating this is a lot of times it was even subjective even in our group internally, so all of us thought differently how to evaluate them. So I'm not saying that these are 100% foolproof and correct measurements, but that's why we try to bring in expert level reviews where it was possible, so to check if they also think that a certain model is better than the other. But the automatic measurements were quite hard to devise.
Thank you. Next question is, similarity search over large clinical databases can be slow. How do you maintain interactive speed while using heavy models like SAM2?
That's also a great question, and it was our concern, or it's still our concern. It's hard to it's important to mention that all these content-based retrieval systems we used has an offline and an online phase, and the heavy lifting happens in the offline phase where you process your reference data with these encoders, and the result is kept in memory because there's usually you have memory to store these feature vectors because these are not that large. And then on the online phase, you only have to do one pass of inference with your query image, and these vision transformers are quite large, but these are just for one single image. These are not slow, and as time progresses, these models becomes sometimes faster. So there are a faster version of these models, and the average hardware of medical devices improves. So I don't see that as an issue. The search part of it, where we actually search in the feature space, that is something that we know that we didn't check thoroughly because our own data set is quite small, like tens of thousands of label data. So KD3 and these 3 methods performed perfectly. But if that becomes larger, or you come to a different project with a already large data, vector database is something that is widely used with extremely large databases, mostly textual. But I think these architectures were implemented multiple times for production uses. So yeah, I don't think that will be an issue if you want to have real time.
Okay, thank you. Well, just to add to that, but if you think of a database inside a hospital, say a hospital have, I don't know, 6,000 pregnancies a year. Each scan, an anomaly scan or dating scan is, say, an anomaly scan, maybe like 30, 40, 50 images. With time, this will grow exponentially. And then, I mean, hugely. And then this vector database becomes also still a bottleneck. There was an interesting research by Stanford published maybe two weeks ago on similar ideas for retrievals in RAG system for agentic system, which showed that when you grow exponentially, your embedding becomes very close to each other. So you might not be able to distinguish lumbar spine, from thoracic spine, or even sagittal spine from axial spine. So it's still a big whole topic that's still an open research problem.
Yeah.
Let's take
Yeah. And
one more
there
question.
is also, okay. And but I just wanted to point out that there is
Yes,
also
please.
very interesting point you mentioned, that it's also a decision that if you want to allow your users to put together a reference database, or
Yeah,
you want to put together a reference database as you know, as a medical company. So that's a tool, and that's also a two ways how you think about it. And if you know, allow your reference data to be grown by the user, yeah, that's also a different set of problems there.
absolutely. So let's take one last question, squeeze in one more. Given that your dataset includes repeated imaging and clinical measurement per patient, did your diagnostic linkage model consider the longitudinal nature of the data?
No, we didn't have this longitudinal nature. So we had, of course, multiple images from one patient, but we specifically limited the search to access the other images from the same exam. So I don't know if that is what the question refers to,
Yeah.
but we simulated the case where your patient comes in, query image comes in, the reference database does not contain that patient or different exams of that patient, and we didn't have multiple examination from the same patient,
The same
so
person.
we
Okay.
didn't have the chance to check that.
Let's squeeze a last question, so it's good to take everyone. How current annotated data could accelerate the annotation timeline?
Sorry, go ahead.
How current annotated
Mhm,
data could
mhm.
accelerate the annotation timeline?
So if you have any kind of annotated data set, a subset of your data, you usually have more unlabeled data than labeled one. You can, if your labeled data is 100% correct and you have a working similarity pipeline with a good model working well in that domain, you can propagate those labels to unlabeled cases. Like in layman terms, it's similar images of your unlabeled data will get the same label as there is already present in your label data. And of course, you still need to check them, these propagated labels, but we found that checking them is much quicker,
Yeah.
especially if you have a high accuracy of this pre-labeling.
Certainly. I think with that, thank you very much, Richie, for the interesting talk. And thank you, everyone, for joining us today. Stay tuned for the next industrial talk for February. And we look forward to seeing you next talk and the one after as well. Richie, thank you very much. It was great to talk to you today. And see you soon. See you later. Bye bye.
It was my pleasure. Thank you. Bye, everyone.
Thank you.